so we start chapter 7. So we are doing chapter 7 lab. So chapter 7 have many methods. We start with the polynomial regression, stepwise, the step functions, and several types of splines. Then after that, local regression and the GAM. So we will cover one by one today. And after that, hopefully we have some exercises. Exercises are only for the splines. So if we do exercise for everything, then it takes maybe 3 lectures or something. So exercise 9 is available on the website. So mostly I'm using my R console, the to-run program, but the chapter 7 lab slides are available on the website, so you can download from Canvas. And my slides are much more comprehensive than textbook. If you see textbooks, you see minimal codes, but my code is more complete with graphics and so on. Okay, so maybe I shared the screen. Sorry, I have so many screens, so okay. Okay, so we are using the Nile river data. So Nile river data is in a default R package, so we can see when you type Nile. Yeah. So we have 100 observations. This is time series data from 1871 to 1917. So we defined that, another variable time, that is from 1871 to 1970. And we try to explain if the Nile River water level has some time trend. And you can see that the level is slightly higher than before 19,000 and possibly slightly higher after 1960. And so probably the pattern is not linear, and probably we have some negative trend here. And after that, maybe flat, maybe slightly increase over time. So we want to identify that. And the last time that we used the polynomial regression, and the optimal degree was, I think that was by AIC, maybe 4 or 7. Actually, I haven't tried more than 7, but the AIC for the fourth degree polynomial that fits well. And this time that I do step functions. So basically we split this data into the 4 different periods, maybe 25 years each. Then we fit the level for each of the 25 years. So the fitted lines are not continuous, but it makes some sense. And to be exact, maybe we have to find the optimal, the knot points to separate several cases. But sometimes the economists say the breakpoint tests. Yeah, so we want to separate this into 4 periods. So the x-axis is pretty simple, 1 observation for 1 year and in total of 100 years. So just 25 years times 4. But in general, if we have the sum some data, that it's convenient to use cut function. So that is that we use the table. Okay, so we use the cut of the time into maybe 4 pieces, then we can get this. Yep. So basically, R defines indicator functions for period. So the first one is 1871 to 1896, and the second one is 1897 to, sorry, the 1871 to 1895, and 1896 to 1920, yeah, and so on. So we have 4 period. So we have the 4 indicator variables. You can see first 25 observations is assigned this category, the 1871 to 19. Actually, probably the 189695. Yeah. And the next 25 observations are in the next category, and the next 25 another category, and the last 25 observations last category. So are they automatically define factor variables with 4 levels. So if we have indicator variable for those 4 levels, we can simply use those factor variables to get the step function regression. So if we summarize this, cut the time 4 into this, then we can see that we have 4 levels. Yeah, it's a little bit hard to see what this means because it's rounded. So 1871 to 1896, but it's rounded up to 1900. But in reality, this is 1896. Okay, so we have 4 levels and 25 observations each. So we can fit the step function. So we fit the Nile river water level on this indicator function. So time 4. So maybe you can see the summary of this linear function. So sorry, I name it LS, so I have to see summary. LS2. Yeah. So you can see that the intercept is 1095. So this is the level for basically the first category. You can see that in the first quarter century, the level is around 1100, and you can see the intercept is 1100. And the second level is negative 222. So that means 222 lower than the baseline. So 873 lower than the baseline. So always, yeah, many students have trouble to understand these questions. So this means that it's negative 202 lower than the baseline. So that means the 873. So you can see that from the 1896 to 915, right? 15, no, maybe 920, 1920. So in this period, averages you can see about 900, and actually it's estimated as 873. And the next period, almost the same level. So you can see negative 268. So negative 268 lower than the baseline. So that means 827. So slightly lower, but they're similar. And last period actually slightly higher. So negative 213. So that is negative 213 lower than 1095. So 882. So it's slightly higher. So you can see this. Yeah. Yeah, so this is the case that we have the 4 levels. And but also that we can try the other things. There may be 2 levels, 3 levels, 4 levels. If only 1 level, then that is just we fit the constant in linear regression. So yeah, now we want to try what number of pieces is the best. We have 4 pieces here, but what number is the best? We want to investigate. So at first, we prepare some object to store all results. So this is the list with empty contents. So we can put anything here. So LS is the list of step function regression. Then we also prepare the AIC.ls. So this is the vector of 10 numbers. So list of AICs. So we prepared these objects. So numeric 10 is just a vector of 10 numbers, and the default values are 0. And at first, we fill out the first object in LS object. LS is a list, so that is the kind of the list of objects. So the first object is defined as Nile river water level on just constant. That means the step function, just one step function is to be used. So 0 naught. So this is a kind of trivial, the model. And then maybe we also calculate AIC. So AIC value is the AIC value of this model. So AIC, archaic information criterion of LSI, LS1. So now AIC LS is this. And LS, the first object is this, the trivial linear regression. Then now that we try the step function regression for 1 knot to 9 knots, or 2 parameters to 10 parameters. So for I is equal to 2 to 10, we define ith object as the LM Nile on just I pieces of factor variables. Then we can fit the step function regression from I is equal to 2 to 10 at once. Then after that, we save the AIC value of that object. In this AIC.ls object vector. And we run this. Then we now run basically 10 regressions. So regression with intercept, regression with step function with 1 knot, 2 knots, 3 knots, and up to 9 knots. 9 knots means we have 10 pieces. Yeah, and you can see AIC value of this. So you can see this. So actually, the 1 knot is better than the 0 knot, and the 2 knot is 2 knots is better than 1 knot, and the 3 knots is still better. After that, actually, it gets worse. And actually, 6, it's almost close to this, but not better than that. So probably this is the best one. So we have 3 knots. So actually, the regression I fit here is the best. You can see graphs. So if you type plot type Nile, you will see just scatter plot, and we want to overlay these fitted lines. So basically in our graphics, we have 2 levels of graphic functions. So one is this kind of entire high level function, so which makes the one figure. And other object, so the second type of functions is the add-ons. So we add some lines or we add some explanations on the existing figure. And the lines function is such a function. And we type the lines times time, and we can get the fitted value of this one. So LS is anyway the linear model, so we can use fitted function. And yeah, maybe I will say maybe 2. And the yeah, maybe I use the color 2. Color 2 is red. So if we type this, then we can get this. So we fit the first, we fit some constant for the first 50 years, and we fit another constant for the last 50 years. So this is the fitted line. And you can do that for I is equal to 3, and color 3 is green, and we see this. So this. So this one and this one and this one. You can see that the first 33 years at a higher level, but the next 33 years and the last 33 years almost the same. How about 4? Color 4 is blue. So you can see this is highest level, and this is lower, this is even lower, and this is slightly higher. Yeah, maybe you can do 9. Color 9, I don't know if it exists or not. Yeah, probably it goes back to black. And this one. Okay. So it goes up and down. You can see that maybe the first 1/3, so that means the 33 years, the level is higher and also level is decreasing. After that, the almost no tendency. The slightly changes over time, but it's not really clear. So in this way, you can see the fitted curves. Yeah. In the midterm 2, one student makes scatter plot of 101 observations by using 101 colors. So the R has, I think it's probably around 600 ready-made colors. So if you use it in a good way, you can make colorful graphs. But the color, the number can be used only for maybe 1 to 8. Otherwise, you have to search for some options. I think some colors function have more colors. Yeah. Do you have any questions? Okay, so also sometimes practically you don't want to separate these 100 years into equal intervals. You can see that probably the first several years it's at a higher level, but after that it's flat. So probably you don't want to use 9 levels, even if we have 8. Sorry, we don't want to use the 9 knots, even if we fit the complicated curve. Probably maybe first 11 years, next 11 years, and next 11 years, and just 1 level for the other. So we want to optimize the knot points. And we don't have much statistical theory on that. We can numerically optimize it, but that isn't easy because the model is not linear. But you can do some experiment. For example, we see this figure, and okay, so about first 30 years, the level is higher. And to be exact, you can see that about these observations, for example, this one, this one, this one, maybe possibly this one. So these ones are not really high. So probably the first 28 or so at higher level, and rest is at a lower level. So if you want to optimize it, possibly that you can define the indicator function for first 28 years and the last 72 years. And we define this as the step function 1. So we want to optimize the threshold. And the next level, I decided 28, then around here, it's slightly lower than other levels. So you can see that these observations are relatively large, but these observations are relatively small. So I decided to make next 14 years as a larger number. So just the 29th to 42nd observations, we prepare one indicator function. So it's pretty ad hoc, but this is step function too. And the next one, this is even more ad hoc, but you can see this is one outlier here. Right? So we just, this is so different from other observations. So we just want to exclude it. So the step function 3 is exclusively for this 43-second observation. Sorry, the 1, 1. And the rest is the 57 observations, I think. And this is step function 3, number 3. And then the rest of the observations are the period 4, so 57 years. So this is step 4. Okay, then okay, so we prepared 4 factor level functions, but the sum of this is equal to 1, right? So S1 plus S2 plus S3 plus S4. This is just 1. So this is the same as the intercept. So we shouldn't include this. So maybe we can use just S1, S2, S3 to regress Nile river water level. So maybe we define a new linear model, Nile, on S1 and S2 and S3. Then AIC value is the 1251. So that is much lower than our previous model with the 3 knots. This is the AIC value of the 1271. So even 20 lower than that. So maybe we can plot this. Then this. So it looks much better, and it's pretty ad hoc, but it looks much better. So basically, we optimized the threshold. So we literally use the 3 new parameters. So 3 thresholds are optimized, but these are not really the linear coefficients. So it's hard to see how to penalize it. So if you want to use this kind of model, then basically you have to do more numerical evaluation, such as cross validation. But the time series data, we cannot do cross validation, so it's really hard. So time series is, in some sense, not really a science. Time series analysis is not a science. So, but it looks much better, right? So, and this is actually the what we do in real life. So, oh, okay, so the level is flat here, but the one, outlier here. Yeah. But this AIC is basically underestimated, right? Because we optimized the threshold, but that wasn't penalized in AIC. If AIC, we increase the number of variables, that is penalized by 2. But so each additional variable has a penalty of 2. But we optimized the threshold, but it didn't penalize it. So the model didn't penalize the optimized threshold. So at least this is underestimated. But even we use the 3 optimized parameters. Usually one parameter that corresponds to AIC of 2. So if we add 6 to this, still 1, 2, 5, 7, So probably it is a reasonable model, but it's really hard. If this is not the time series data, then you can do cross validation to see which model is better. Maybe one possible way is to do maybe training and test approach. We just randomly separate this into two, training set and a test set, and using a training set you fit the data, then using the test set you test. So that's possible. But yeah, generally time series, it's hard to apply those methods. So practically, this may work. Statistically, it's hard to evaluate whether or not this is a better model than the previous one. It looks pretty ad hoc. Okay, so do you have any questions? Okay, so next one is the basis splines. No, sorry, the basic functions, basis functions. I think there is a typo in the slides. The lab, lecture notes, the basic functions, but this should be basis functions. So 7.3, the basis functions. So remember, what is the basis function? So basically, we have y is equal to the beta 0 plus beta 1x plus beta 2x. So this is a linear function, right? But the beta 1 x1 and the beta 2 x2. But this x1 and x2, that can be any function. So, maybe I would say that maybe just a polynomial regression, we can think about it. And the polynomial regression is here, but this is x squared and this is x, but it doesn't have to be x and x squared. For example, it can be cosine of x and the sine of x. In this way, probably we can fit the model better if the data is periodic. And here, we don't really have reason to believe that the Nile river water level data is periodic, but just as an experiment that we fit sine curve and cosine curve. It has some benefit even if it's not periodic. For example, x squared blows up when x goes to infinity, but the cosine x and the sine x do not. So we define the several curves. So one is the cosine curve, time. Okay, so we standardize it. So time minus 1870. It doesn't make much difference if we just use time. And we want to make the period as 200. So basically, we make the one arch for 100 years to fit the data. That makes some sense, right? So if the period of cosine function is 200, then for 100 years, it looks like mound shaped. So it's similar to parabola. So it makes some sense. And yeah, we subtract time minus this. So this has 100 elements. So first 6 are here. So it slowly change. It is slowly changing because it's the cosine function with period of 200. And we also define the sine function to control the phase and the size of the the magnitude of the curve. So sine of time minus this one and this. Yeah, and this is also the slowly changing variable. And the C2 cosine curve with higher frequency. So period of 100, frequency is twice as large. And also S2. So this is the cosine. Sine is this and cosine should be this. And we fit the data, but you can see that the Nile River water level data is from 600 to 1400. And also the level, average level is about 900. So we wanna adjust the mean and the standard deviation to see how these curves look like compared to the original scatter plot. So we just adjust the mean and the standard deviation to make it comparable to the regression curve. It's not necessary to do regression, but just that we want to see these curves on the scatter plot. So we adjust the mean and the standard deviation. I make standard deviation of 300 and the mean of the mean level of Nile River water level, Nile River water level. So we define these functions. So standard deviation is set at 300 because the range is about 800. So if standard deviation is 300, that means most observations are within the range of 600. So it's somewhat reasonable to compare it with the original scatter plot. Okay, so we do the same thing for the higher frequency one. So C2G is the transformed C2 and S2G is transformed S2. Then over this one, you can see the lines time C1G and color one. Then you can see that this. So original data, and this is the cosine curve with the period of 200. You can see if we continue this in the 2070, it goes back to the original level. Okay, so that this is just a half of cosine curve. And we are using some other curves. So now that I put the 4 curves, so yeah, so the red one is the sine curve with period of 200, and the green one is cosine curve with period of 100. So just the one period in 100 years. And the blue one is sine curve with period of 100. And if we use these 4 curves, probably we can get reasonably good fitted line. Okay, so now that we will fit. So LB2 basis function, we fit Nile on S1, C1, C2, and S2. You can fit the C1G, S1G, C2G, S2G, but anyway, this is just linear transformation, so you can do either way. AIC is what? The AIC is the 1274. So that is comparable to step functions without manipulating knot points. So yeah, and also you can plot the time Nile and the lines time fitted of LB2. So you can see this. So somewhat it's natural, right? So that we don't have any bump and we don't have feature to blow up when x goes to infinity or negative infinity. So of course this is periodic curve. So and we don't have any reason to believe that this is periodic. So maybe yeah, it's somewhat not reasonable, but yeah, at least it fits the data somewhat well. Extrapolation may have trouble, but the interpolation may be good enough, even though we don't have any other points. So for example, this data is maybe observed only every 3 years or so. Then we wanna, interpolate the missing years. Then probably this method works well. Any questions? So I don't know what kind of functions are available to define basis functions. So, yeah, step function is a special type of basis function, polynomial regression, sine, cosine, possibly maybe square root or so. It may be good because it does not blow up when x goes to infinity. But if x goes to negative infinity, we have trouble. So I don't know. Yeah. Okay, so then next one is regression spline. So we use the library splines, library splines that you can download it. And the basis functions, the regression splines is also another form of the basis functions. And we need knot points. And here, simply that we use these knot points because we want to separate it into, 4 pieces in this case. And at first, we define basis functions based on these knots. So we have 3 knots. So we have basically 4 variables. So yeah, sorry, not 4 variables. So we separate it into 4 pieces. The first piece that we fit the 3-degree polynomial. So that means we have 4 degrees of freedom: the constant and the linear term, quadratic term, and the cubic term. And the second component, we have just one additional component, because originally we have 4 components, but we require that it's continuous and smooth, and the second derivative coincides at knots. So we have only one additional parameter. And period 3, 1 additional, period 4, 1 additional. So 4 plus 1 plus 1 plus 1. So we have 6 variables, including the intercept. So if we define the basis functions using these BS functions, actually, so this has the 6 columns. So intercept has been dropped because it's trivial. So the linear term, you can see this is linear, 0. Not really. Not really linear because it's somewhat linearly transformed. So the function 1, 2, 3, the variable 1, 2, 3, this corresponds to the linear term, quadratic term, and the cubic term for the first period. And the next one is the quadratic term for the second period. So the first 25 observations or so, that this is equal to 0. And after that, it becomes non-zero. And the 5th and the 6th are prepared to add some cubic component for the 3rd period and the 4th period. So that's why we have 6 components. Okay. Yeah. So we have 4 plus 1 plus 1 plus 1 parameters. 4 periods. The intercept is ignored here. So we have 6 columns. So yeah, so now we fit the data model. So we have the 6 variables. So I define this as LRS6. So Nile liver water level on this BS time with this knot, with these knots. Knots is equal to xi. So 3 knots, cubic spline. So LRS6. So AIC of LRS6, this is what? This is the 1277. So it's comparable to the previous one. So it's actually slightly worse than the best step function, but we haven't optimized the number of nodes. So that's pretty natural. So 1277. So again, we may see the figure. So always it's good to see the fitted curve to make sure that your code is correct. And actually this, it looks very similar to the previous one, but I think that we didn't have any error. So this is the fitted line. So this is regression spline. Fitted, yeah. Yep. And also we can add the confidence band for this fitted line. So if we define the predicted value of this model, with standard error information, then we can get actually the standard errors. So you can see the fitted values as well as the standard error of fitted value. So if we use this information, then you can make the confidence band. And the confidence band maybe should be drawn by using the t-distribution, but here I just use the normal approximation and the plus minus 2 standard errors to make the confidence band. So we add lines of the predicted value. The predicted dollar fit, this makes actually the same values as fitted of LRS6. So it doesn't change because it's overlaid. Maybe, yeah, maybe slightly thicker because we draw a line twice. And the plus minus 2 standard deviation. So 2 times the predicted value, the standard error. Yes, and maybe we change the line type to the dashed line. Something is predicted 2 times. Then we can see this upper bound. So this is the fitted line plus 2 standard error. Also, we can draw the minus 2 standard error. So this is the fitted curve. So you can see that if parameter changes a little bit, then the fitted value changes a lot on the end of the period. So that makes at the end the standard error gets larger, and also this end it's larger. But in the middle we have the smaller standard error even around the knots, because around the knots basically we have 2 informations, right? So basically the curve for the first 25 years and the next 25 years, and they use both information to make a smooth curve. So standard error doesn't get larger. But here at the end point and at the end point, standard error gets larger. Yeah, and also the head NS function, natural spline function, makes similar things to the BS function. And yeah, I think it takes some time, so I will not show it. But basically, this uses the orthogonal basis. So I will show just the resulting curves. Okay, so this is chapter 7 slides. And if we use this NS function, the natural spline functions, we have these 6 orthogonal bases. So if you calculate the correlation between these 6 components, any of these, the 2 of these 6 components, then that correlation should be 0. So it's slightly hard to see which the figure. So I don't know. So for example, this curve continues to what? I don't know, maybe this one. I don't know, maybe I should differentiate the colors. But if we differentiate colors, then you can see that these 6 components are orthogonal. So we have less trouble with multi-collinearity, and also the less trouble to have the 2 large values on the both sides, both ends. So basically, it behaves better. It behaves better than the previous, the BS function, but essentially it's just a linear transformation of BS. So that should be fine. That should be the same. The result, fitted curve, should be the same. So each basis are transformed so that it's orthogonal. Okay. So yeah, I think we have to differentiate color. Why I didn't do that, I'm not sure. Do you have any questions? So these are within the linear regression. So to see how many components is the optimal, that you have to do cross validation, or maybe you have to calculate AIC or something like that. And the next one is smoothing spline. So remember that the choosing knots is not easy. So we want to avoid it, and the smoothing splines avoid the choice of knots. So basically, we prepare many knots. So if we have n observations, we prepare n-1 knots. That is the maximum number of knots, right? So then, but we penalize the smoothness of the curve. So the resulting curve is smooth enough, even if we have many knots. Yeah, so we use the smoothing spline curve, smooth spline function, smooth dot spline function in the splines library. Here, we only have to specify the degrees of freedom, so df2, for example. Then we return this, and this is a more complicated algorithm to fit. Right, so we penalize the smoothness of the curve. So it's similar to rich regression or lasso. So we cannot use AIC. We cannot use the we cannot use, yeah, at least we cannot use AIC. So it reports the generalized cross-validation value. So this is similar to the cross-validation error, but it uses some approximation to the CV, so that it's faster. So basically, this is leave one out cross-validation under special circumstances. General case, it's an approximation to the leave one out cross-validation. So that is GCV. So it's convenient that the reports GCV there automatically, so we can compare the graphs. So for example, if we use more knots, maybe we make the degrees of freedom 3. Degrees of freedom is 2. That means it corresponds to a straight line. Right? So intercept plus slope. And degree 3, that is corresponds to cubic curve if we use polynomial regression. So you can see the GCV. So GCV gets smaller, actually, so much smaller here. So actually, the degree 3 is better than degree 2, and so on. We can increase it to more, maybe like 8, or maybe I don't know, maybe 6 or 8. And you can use the AIC function. I think the AIC may not work. AIC, I think some special name. AIC what? Sorry, the GCV. GCV we have to extract. So SS3 CV maybe CV it works. Yeah, CV. I think the CV criterion, that is the exact name. So if we do SS8, then we can extract. Actually, the AIC is much smaller. And also, this function, smooth.spline, has functionality to optimize the CV. So CV is equal to true. Then SSCV, this. So you can see optimal lambda value. Lambda value is some penalizing parameter, hyperparameter. And the equivalent degrees of freedom is 23.45. That corresponds to 22-degree polynomial. And the ROCV is the 17,646. So this is optimized result. So we can plot the result. So time Nile. And this is the scatter plot here. And we overlay optimal smoothing spline curve 5. Yeah, so this. It looks too complicated, but the, statistically speaking, this is the optimal model. Maybe we can fit a simpler one, SS2. SST corresponds to 2 parameters. So that means that we don't allow any, curvature here. So it becomes a straight line. And the SS3 here. SS3, that corresponds to the quadratic curve, but it penalizes smoothness in a different way. So it's not really the quadratic curve, but it has similar level of smoothness to quadratic curve, and you can see it. And this, the light blue one, is optimal in terms of CV, cross-validated error, and GCB to be exact. Sorry, I think it takes so much time for this, but yeah. Do you have any questions? Yeah, I think that, yeah, so theoretically we can apply just cross-validation here, but probably it takes too much time. Spline is more complicated algorithm than linear model. So they don't want to calculate the, regression, do the regression so many times. It takes too much time. So we use some approximation method, the GCB, to evaluate the model. Yeah, so slightly different criterion is needed for regression spline and the smoothing spline. Regression spline is just a traditional, the frequentist approach model. So we can calculate AIC. Smoothing spline, it corresponds to Bayesian method. We have a hyperparameter, so we cannot calculate AIC. So we have to rely on cross-validation or generalized cross-validation. Any questions? So next one is local regression. So this is entirely different method because this is non-parametric method. And we use the LOESS lowest function for local regression. I think probably this is also in smoothing spline function. Help LOESS. Sorry, this is in the original base package. So local polynomial regression fitting. So this is in the original R package, default R package. So so local regression. We fit Nile on time. And this span means how many observations to be used. So we use the 20% of observations to fit the data, 20% closest observations to fit the regression model. So this is the lowest. And yeah. Probably we have other parameters such as what weight function to use and the weight function. Yeah, I think these two parameters. So weight function also we can change. In default, probably we did not use any weight function. So you can see that the weights yeah, so weights are optional, so we don't use weight here. So just we choose the 20% closest observation to fit the model. And also regression model, we need the specification, but the I believe that the linear function for each component is the default. And if you want to use the more complicated one, maybe you can choose the model subset any formula. Really not. Gaussian method. Yeah, here, degree. So degree 1 is the default, I believe. The degree 2, sorry, degree 2 is the default. So, sorry, the degree 2 is the default. So at each point that we fit the quadratic regression with using the 20% of data in this case. And we can change it into 1 or 0, even 3. I don't know. Normally 1 or 2. So maybe you can use a larger value. But generally, it's not needed. Probably 1 is sufficient in most cases. And default is 2. Then we can see this. So local regression doesn't have any theory. So basically it smoothes the curve. So we use just the similar observations and take average. That is the idea. So we don't have any theory behind it, but the still you can, for example, calculate the error size. So you can do cross validation to see which model is the best. So here, I don't optimize the parameter, hyperparameter, but I try several patterns. Local regression with 20% of closest observations, nearest observations, and 50% observations and 80% observations. So remember that this number is larger. We use more observations. So that means the resulting curve is smoother. If just we fit the one regression model for entire data set. So smaller span. Span is proportion of data used. Means the more, more complicated. Yeah, so plot of time Nile. So this is original plot, and we can overlay line fitted and the LOEO and the color one. Then we fit the first one. So this is the So this is the span 0.2. Right? So it's a pretty flexible curve. So it's not smooth curve. And the LOEO5 uses 50% of observations, so it becomes smoother. So red one. And 80% color 3. So it's even smoother. So I don't know which is the best. Maybe the black one is the too volatile. So maybe red one is more practical. So I haven't tested this, but we can do this. You can use maybe cross-validation to see what's the optimal parameters. Do you have any questions? Okay, so now that we go to the multivariate case, so generalized additive models, GAMs. And we use the ISLR library to use the wage data. And we use the library Gam to fit the function Gam. And wage data, remember that the wage data includes several variables: wage by age and year, marital status, race, educational level, the religion, and the jobless status, and job class, or the job class, and the health condition, and health insurance, and the yeah, this is wage, log of wage and the wage. And yeah, you can see the pairs. You can use the pairs functions to see the overall only one column is in the argument in, oh, sorry, the wage W. Yep. Yeah, so we can make it. But these plots does not make sense because anyway, so we only have 5 levels for marital status. 5 levels, yep. And the health insurance, we have only 2 levels. So just 10 plots. So it's not informative. So sometimes we can use the jitter function to differentiate the overlaid points. So in our case, especially we want to see the relationship between year and some other variables such as wage. So we can use the jitter function. So jitter function adds some noise. Sorry, just a moment, please. Sorry. So we attach the wage data frame and then wage data frame. Then we attach. Sorry. Then we put the jitter function. And we calculate the pairs of several variables, maybe wage and age and the year.jitter and the education. Then we can get this. You can see that we have several years from 2003 to 2009, but we add artificial noise so that we can see how many observations are here and here and here. Sorry, still we have too many observations, so we cannot really see how many observations are here. But if data is slightly smaller, this is useful to see how many observations are observed for each year, and to see more tendency between variables. Particularly if we have 2 categorical variables, this is certainly the most useful methods. Maybe education, you can also add this noise. Maybe education, J, jitter, education 1. This should be numeric, so maybe like this. And pairs education J, then we can use this figure. So still, maybe we have too many points, so we cannot really see how many observations here and how many observations here. But a smaller number of data points that we can see there where we see more data points. Okay, so now that we fit the generalized additive models, so generalized additive models that we can basically use the we have several methods. Yeah, so the one way is we can fit the wage on other variables by linear model function, but we specify each curve type for each variable. For example, we use the natural spline with 4 degrees of freedom. Sorry, the natural spline with the 4 knots and 4 components. Sorry, 4 components, and the natural spline with the 5 components for age, and maybe educational level is the factor variable. So just we put it as is. Then we can fit the usual model. But this yeah, so this is one way, and another way is to use the Gam function. Yeah, another way is to use the Gam function. So it has some more options, but basically we do the same thing. So Gam and is the wage on the natural spline of ear. Maybe this time we fit the different model. So NSH 3 and education and data wage. Then we get this. So basically these are the same, but some diagnostics are little more detailed and sometimes more convenient. So it returns the ANOVA table for this. Yeah. And it says that this is sequential one, so it's not okay. So at first we see if the second degree polynomial of ear is useful or not, and overall it's highly significant. And additional variable age, actually even we have already used ear, the age is more important variable with smaller p-value, and education also more important variable. So from this, we can say that the education is probably most significant, and age maybe next based on F value. And this one slightly less, but still it's highly significant. If we change the order, maybe maybe the situation is different, because this is sequential. And we have some other options to make, for example, the figures. So parameters MF row. Okay, so we put some profile marginal functions, marginal plots. So with this GAM objects, we can create this kind of figures. So we can see all marginal functions at once. So this is the ear, and this is the fitted value of ear. So you can see that the year 2003 to 2009, the wage is increasing over time, but the increase is smaller in the recession from 2008 to 2009, maybe 2007 to 9. And age, actually the peak is about 45, and the wage is getting lower after that. And before that, it's lower also. Educational level, high school, less than high school graduate, lowest, and the high school graduate, some college, graduate school. Yeah, certainly we have a difference between these. So these features, such as ANOVA table or these figures, are useful, and we cannot generate this figure at once with LM function. So sometimes this is useful. Yeah. So this is the GAM. Yeah. And also smoothing spline can be used by using S function. So smoothing spline function is originally smooth. Sorry, the spline.smooth, so spline, smooth.spline function. But within GAM function, the function S, lowercase s, that works as the smooth.spline. So that is also included in the slides. I mean, included in the lecture note, so you can try that. Yeah. Sorry, I didn't have enough time to explain the exercise, but the next time that we do some exercise, then after that we go to chapter 9, chapter 8. Okay. So do you have any questions? No? Okay, so see you next week.
Okay, pleasure. Thank you. Have a good day.